Hello everyone, this is Sumedha Govindappagari uh, from MTech Signal Processing, and I want to give a summary of my project, which is on implementation and study of Bluetooth Low Energy and summary. Uh, I've done this project under the guidance of Professor Nilesh B. Mehta. So this is the outline of this presentation. So what I'll be presenting. So what is Bluetooth Low Energy? Bluetooth Low Energy is a low power wireless communication technology operating in the 2.4 gigahertz ISM band and standardized by the Bluetooth Special Interest Group. BLE is basically designed to support short range, low data rate communication with minimal energy consumption, which has led to its widespread adoption in wearable devices, asset tracking, smart sensors, healthcare systems, and also IoT applications. So Bluetooth Low Energy has like many versions. There has been the 4.0 version, the 5.1 version, but both of the versions, when it comes to them, um, they've not been accurate with their results regarding the distance estimation between two devices because they suffer from multipath propagation and also the implementation of them of those two versions is very complex. So this has led to the implementation of the Bluetooth Low Energy 6.0 version, which is called channel sounding method, where this method basically uses 79 RF channels on this 2.4 gigahertz ISM band, and the frequency spacing between these channels is 1 megahertz. So here, as we can see, the devices which we'll be using is the initiator and the reflector. So the initiator is the one which connects to the reflector. It sends out connection, and reflector is the one which responds to the connection. And initiator is also the one which calculates or estimates the distance between these two devices. So channel sounding basically has two methods. One is the round trip time method, and the other one is the phase-based ranging method, which we'll be discussing. So as we can see, the whole channel sounding operates between these two devices, and also the measurements. The whole procedure is organized into the whole procedure has multiple events, as we can see in this diagram. Um, One event is has many sub events, and a sub event has multiple steps. Now, step, as we can see, is it is the basic transmission and reception between the two devices. Like one step has a transmission reception between the two devices, and here, like the distance is estimated on multiple steps, and this helps in accurately estimating the distance. Now, each step has different modes. When I say mode, it has different functions. So when we say mode zero is the most important one. It has to be implemented. It is very necessary for the frequency offset calibration because when we are implementing it practically, we'll be having frequency offsets between the two devices. So to calculate the frequency offset and compensate the frequency offset for accurate distance measurements, we'll be using this mode. And mode one is the round trip time method, and mode two is the phase-based ranging method, and mode three is an optional method where it is a hybrid of this round trip time and phase-based ranging. Now, when we go to mode one, that is round trip time, so we will be using a CS sync packet, as we can see the diagram here. So the CS sync packet has a preamble, it has an access address, it has a trailer, and also the sounding or random sequence. So this packet is basically sent from the initiator first. So and it will be received at the reflector, and then after a certain amount of time, the reflector again sends back the packet to the initiator. So during this whole process, during this whole round trip time, we'll be timestamping four different like the departure time at both the devices and also the arrival time at both the devices, using which we'll be calculating the whole round trip time. And from the round trip time, we'll be estimating the distance using this form. So that is the round trip time method. And we have the phase-based ranging method, where in this phase-based ranging method, we'll be using an unmodulated carrier wave called the CS tone. And this is sent from the initiator to the reflector. And reflector, it based on the propagation delay and what channel we are using, it will be making some phase measurements. And again, the CS tone is sent from the reflector to the initiator. Initiator calculates its own phase measurements, and using the two phase measurements and their difference, we'll be calculating the distance here. Um, so the maximum distance we can estimate using this procedure is 150 meters, because the frequency spacing between different channels, the two any two channels is 1 megahertz. So we'll be getting a range ambiguity of 150 meters. So in this project, we've done simulations of this PBR and RTT. And also, as we can see, we've used two 5 modes called the LE1M mode and the LE2M mode. So LE1M and LE2M, they differ in the symbol rate. So LE1M will be sending packets or tones at 1 megasymbols per second, and LE2M will be sending it at 2 megasymbols per second. And the performance metric that we've used for the plots is RMSE. And also, we have done the simulations in AWGN channel, and also we've implemented how the plots work under frequency offset or phase noise, path loss, and also Bayesian multipath channel. So as you can see, these are the plots for AWGN. Uh, the RMSE basically decreases with has SNR basically increases, and L here is a number of samples for the two modes. As you can see for LE1M and LE2M. And here we have how the RMSE behaves as we increase the number of packet trials for Monte Carlo simulations. And this is the impact of frequency offset. So the frequency offset here, I've taken it to be 40 kilohertz. Uh, this is the impact of phase noise. Um, Here I've taken Ryzen channel. We've defined the environment, the path delays, and also the average gain. And based on the average gains and the path delays we've used, we get this plot where the K factor is taken to be 10. And these are the plots for the path loss. And as you can see, uh, RMSE is increasing as we decrease the RMSE is increasing as we increase the path exponential, and also it is decreasing as we increase the transmit power. Yes. So these are the conclusions. We have implemented both the RTT and PBR methods, and we've derived the RMSE expressions, and also evaluated the performance under different wireless impairments. And future work is we can, after calculating the frequency offset, is compensating the frequency offset for more accurate measurements, and also implementing mode 3 and also WLAN interference analysis. Thank you.